So this short video is going to just kind of review this PowerPoint. I still want you to go through it yourself. So download it and put it in presentation mode is usually the best way to view these. But I'm going to kind of blaze through some of the highlights here. But so now that you know a little bit about where igneous rocks form and how we get magma, we want to talk about naming these types of rocks and figuring out what information we can learn from our igneous rocks. And so if we look at what's called a rock cycle, it's just the relationship between the different rock types that we're going to talk about. So for this week and next week, we'll focus on igneous rocks. There are kind of two categories here. They're all formed from molten rock. That's the definition of an igneous rock. But there are a subset that cools inside the earth, and we call those plutonic igneous rocks. And there's a subset that cools on the surface of the earth. We call those volcanic igneous rocks. And this week, we're covering all of igneous rocks with a little emphasis on plutonic. And then next week, we'll focus a little more on the volcanic side. So the lab will cover just the plutonic rocks this week, and next week it'll cover the volcanic rocks. But in this lecture, we're going to talk about both kind of interchangeably back and forth. And so the cycle here just explains or shows how we can turn one rock into another, right? Any igneous rock can be weathered, and then the pieces can be glued together and we get a sedimentary rock, or any rock can be heated and squished and turned into a metamorphic rock, and all those kind of relationships that we can kind of talk about in the future. So the first couple slides on the presentation are really just a review about what I just talked about in the video previously about where is the magma. And so we get different types of melting at different boundaries. Divergent, we said, was decompression because of convection in the mantle. And so there's a term here called mafic, which is I'll introduce or kind of elaborate on in just a couple minutes in the next couple slides. But it's a composition term that we use to describe what makes up the different materials that we get. And so the ocean crust is what we call mafic, has a certain minerals that are there and certain elements. We also get hot spots. You can get lots of different compositions here depending on what's melting. Some examples, of course, of hot spots are Hawaii and Yellowstone. And then we said the other place we get magma is where we have subduction because we're adding some water there that's changing the chemistry, causing those things to melt. Okay, so how do we look at igneous rocks and say, yes, we want to label those? Well, of course, we need a chart, which you'll see about how to name things, right? But the two main ways we're going to observe igneous rocks and figure out what they are is through texture, right? So the main two textures that we're going to introduce initially are just coarse and fine, right? So coarse means that I can see the individual crystals easily with my naked eye. We're going to argue that the samples on the right are coarsely crystalline. Samples on the left are finely crystalline. And so on the right, I can see each crystal with my naked eye pretty easily, even though their colors are different. On the left, I get it. You can see little polka dots or little dots in there. Yeah, they are crystals, but they're tiny. And the remainder of the rock, let's say we're looking at the dark black one at the top. Yeah, I can see little lighter dots there, but all the black stuff is all so small I can't see the individual crystals, and vice versa for the lighter colored rock on the bottom. So fine and coarse are two textures that we want to be able to identify, and they tell us something. Coarse means it cooled inside the earth. The idea is that cooled slowly. The magma never made it to the surface. It was insulated by the kilometers of rock that were around it, and so the heat dissipates extremely slowly, allows the crystals to grow fairly large, where on the finely crystalline rocks, they make it to the surface. There's a huge temperature difference between the lava and the air. They cool relatively quickly. Crystals don't have time to get very large. And so we associate the size of the crystals with where it cooled, but it's also being used to name the sample. So we want to be able to identify those textures. We're also going to look at composition, though in this case, we're going to associate color is going to help us with composition. So we're going to look at light and dark. So the darker they are, they have different minerals. The lighter they are, they have other minerals that are common to the rocks. And so we can use that once again to name them. So here's the terms that we're going to use when we talk about composition of igneous rock. So the red terms on the left there, mafic, intermediate, and felsic. We only use these for igneous rocks, but they're composition terms. And so for volcanic rocks, it's a little easier. We're just using their overall color. So the dark black rocks that we see are typically what's called mafic. They have a lot of iron and magnesium. They make a lot of dark minerals, so the rock has an overall dark appearance. On the other end of the spectrum, at the bottom here, the term felsic are the really light colored rocks. And so for volcanic rocks, they would be tan to light gray, and those have lots of quartz and sodium plagioclase and things like that that form light colored minerals. And then, of course, the intermediate. And so typically what happens is, given 3 samples, you would be able to pick them out because you could compare the colors. So we do that a lot. So if we were given these 3 images that are all of volcanic rocks and said which one's the mafic one, because we can compare, we'd say, oh, the darkest one must be mafic, the lightest one must be felsic, and the one in the middle must be intermediate. And those would all be accurate statements based on that. So, of course, if we were in a classroom, we could give you the samples, you'd look at all 3. So in the lab, we're going to just give you images, and you're going to try to figure out what's the composition. Because if it's finely crystalline, like that top sample, and mafic, we would look at a chart and it would tell us the name is basalt. Okay, or if it is finely crystalline and super light, we're going to give it the felsic name. We look at our chart, it would tell us it's a rhyolite. Okay, plutonic rocks are slightly different because the crystals are large. We're just looking at how much of the rock is composed of dark or black minerals. So if there's a lot in there, we're going to call it mafic. If there's hardly any, we're going to call it felsic. And if it's somewhere in the middle, we're going to call it intermediate. So that's how we're going to use composition and color, right? We're going to say that color is equating to composition in a general term. And those composition terms are mafic, intermediate, and felsic. That's what we want to use when we talk about composition for igneous rocks. So I'm going to kind of cruise through this a little bit, but here's the idea of crystal size, right? Big and small we're going to use. Tell us something about how they cooled. We talked about that already. And then light versus dark, right? That's going to give us some composition stuff. It tells us what is melting. Okay, so let's see. So here's the idea that we have finely crystalline rocks that make it to the surface and coarsely crystalline rocks that don't make it to the surface and form deep inside the earth. And so I want you to run through the next slides pretty quickly. I'm going to do that right now, but the idea is that we can look at this, and I showed you this before we talked about minerals, this little Bowen's reaction series. Mafic stuff is up here. It's forming minerals like olivine and pyroxene and calcium plagioclase. These are really dark minerals that are forming. And so this is a mafic rock. It's very dark. Doesn't matter the crystal size, big or small, the dark black, lots of dark black minerals would give us a mafic sample, right? And so we can look as we move cruise really fast. We get intermediate stuff, right? What is that? That's the minerals that show up kind of in the middle here. They form light and dark together. We get kind of a gray sample, or one that has, kind of in between when we're looking at percentage of dark minerals. And then the felsic stuff is the light minerals, mostly light. If they're big crystals like here, there's only a few or a small percentage of black minerals, or the overall color is, light tan, things like that. Lots of quartz and micas in there that compose most of the rock. Those are light colored minerals. All right, what else I got for you? And so where do we get these things from? Well, the general story when we talked about the continental crust and the oceanic crust is that the oceanic crust is very mafic. And so the material we get there is basalts and gabbros. Those are the mafic igneous rocks. Finely crystalline, coarsely crystalline. The mantle is actually a term that I haven't talked about yet, but it's called ultramafic. So it has even more iron and magnesium minerals that form the mantle. And so there is a sample that we see called peridotite that we think makes up most of the mantle. That's where our mafic samples come from. The intermediate stuff in general, we argue, is a mixing of the mafic magmas that we get from subduction and the felsic continental crust. So remember, the Oceanic crust we said was mafic. The continental crust is felsic. And so when we get melts that come out of the mantle here, even though the mantle's ultramafic, we tend to get mafic melts that come out of here because we're partially melting the mantle. That material, we said from before, becomes buoyant because liquid and it rises. And so this is mafic, this is felsic. I can mix them together and I get something in between. So a lot of subduction zones, we get intermediate composition igneous rocks, right? And that's just because of what's melting there. And let's see. And then the felsic stuff is the continental crust. It's almost all felsic stuff, whether it's small crystals or big crystals, or in some cases a new texture, something that has lots of holes in it. And so besides our, let me just jump through here, we said that, right, the crystal size tells us something about where they cooled. There are some other textures we can look at that give us additional information. And so we've got the coarse, we've got the fine, we've also got what's called a glassy texture, which we see in the igneous rock obsidian, suggesting that no crystals have formed here because of the extreme quickness of the cooling of this material. Maybe quenching, maybe going into some type of fluid, water or something could cause it to cool extremely quickly and gives us that glassy texture. We also get a weird texture called porphyritic. This is where we have both big and small. So in general, we would argue we have small or big. Both still tells us a good story. The big crystals formed while it was at depth, and the magma chamber started to crystallize. But before it completely crystallized, there's still some fluid in there, and I have big crystals kind of floating around. There was an eruption that allowed that material to make it to the surface, and the rest of the melt cooled quickly. So 2 stages of cooling here based on crystal size. So we get that texture. Very large crystals like this that are inches big, which is not common, is suggestive of maybe some hydrothermal or the last stages of cooling of a magma, usually on the edges where there's lots of fluids there. And then we get a texture called vesicular, where it has lots of holes. This is telling us that there was a lot of gas dissolved in the magma, and when it made it to the surface and cooled, it cooled around those gases, and then they've since escaped. And so those holes tell us something about the history, right? What happened there. And let's see, I think the last one we got for you is what's called pyroclastic. So there are some rocks that are glued together. So it tells us that it's a pretty violent eruption here. So when we blast some material out of volcanoes, the big pieces are really hot as they come out, and as they land on the ground, they kind of fuse together or weld themselves together. And so we can see individual fragments, and we call that texture pyroclastic. And the clue it gives us here is that it was an explosive eruption. All right, so that's kind of the story of how we're going to identify rocks. It's just texture and composition. When you get to lab, you'll see the little chart and give you the names, and you'll use those kind of things to help you give each sample a name based on your observations.